from Lille, and he's going to talk about hydrodynamics for open ASEP with weak symmetry. Lude, the floor is yours. You can start when you want.
Okay. Thank you very much. And thank you for the introduction. And I'm very happy to have a chance to talk here. So today my talk will be on the hydrodynamic limit of the asymmetric simple exclusion in contact with open boundaries. Okay, so So the talk will, so in this talk will concern the boundary conditions in hydrodynamic limits. So this is so suppose if we have a microscopic dynamics that is attached, so that is attached to the outside world. So something can, for example, the particles or energy can come in or come out from the outside world. Then this kind of dynamics will have some boundary conditions in the macroscopic equation. And for this problem, if the macroscopic equation has a smooth solution, for example, the diffusive equation, then this is quite well understood. And we know that due to the strength of the boundary dynamics, we can have various type of boundary conditions, such as the Dirichlet one, the Neumann one, or the mixed one. However, if the macroscopic equation has non-smooth solution, for example, a hyperbolic conservation law, then we know that typical kinds of discontinuous behavior will appear at the boundaries, which is usually called the boundary layer. And for the microscopic origin of this kind of discontinuity, so our knowledge is actually quite limited. And so today in my talk, I will try to explain some of these kind of discontinuities. Okay. So the microscopic dynamics I want to study is the most classical one. So it's asymmetric simple exclusion with some open boundary. So let's see so now we have a one-dimensional lattice. So this is from 1 to n. So these two are reservoirs. These are out of the dynamics. So in the bulk, so we have the jump rate is p plus sigma to the right and the sigma to the left with the exclusion rule. So I will write the bulk generator is p times the total asymmetric one plus sigma times the symmetric one. So here we see that it's asymmetric to the right. And at the boundary, the particles can come in and comes out from a reservoir. So with the rate is alpha in. So in the left is alpha in, the gamma out. In the right is beta out, delta in. So we can see this kind of boundary generator. So basically it means that if eta 1 is 0, so eta 1 is empty, then I have rate alpha that one particle can come in. If eta 1 is occupied, then with gamma rate it comes out from the system. On the right is the same. So here I would like to mention two ways to choose the boundary rates. So the first one is more or less classical one, and most of the existing results are concerning on this choice. So this is the first made by Thomas Liggett at this very early paper. So the basic idea of this choice is that the particle jumps from the reservoir, so it should jump in accordance to the particle the asymmetric jump rate in the bulk. So what does it mean? It means that so suppose that I have a density rho minus bar here. It's from 0, 1 to 1, and at this position, let's say it's this is eta 0. There's always a possibility of rho minus bar that there is a particle. So then when this particle wants to jump, it jumps with the same rate as here. So when it jumps in, the rate is p plus sigma because it's to the right, times this possibility, rho minus bar. So this is alpha. And similarly, if this one will jump out, so the rate is sigma times the possibility that this site is empty. So it's 1 minus rho minus bar. So this is gamma. And on the other side, it's something similar with a rho plus bar. And of course, you see that if we choose the rate like this, then the finite dynamics is very near to the projection of infinite dynamics with density rho minus bar at the left and the rho plus bar at the right. Okay, so this is one choice. So the other choice is that we want to study the full degrees of freedom. So just any alpha, beta, gamma, delta. So of course, this one would be difficult because this we have some more method. And in this talk, I will mainly focus on this type. So it's a full degree of freedom. And indeed, I want to consider further. So as I mentioned before, the nature of the macroscopic equation, the hyperbolic equation, is that the solution can be non-smooth. Then there's no reason to restrict our discussion for the boundary data to be a smooth, function of time. So here I want to study the boundary data. So it's changing on the macroscopic time, and it's changing non-smoothly. So it is an L infinite function of the time. So this is a boundary data I want to take, so just a L infinite function of time. Then we define this kind of generator. So here, so this n of power theta is a parameter that regulates the strength of the boundary reservoir. So if theta is positive, then the jump between the reservoir and the jump to and from the reservoir happens more frequently than the bulk. So it's a faster reservoir. If theta is minus, then it's slow reservoir. And here I have another parameter lambda, which is from 0 to 1. And I use this parameter to speed up the symmetric part. So this is a technical thing that if I speed up this one, then it gives me a better convergence to the equilibrium. So this is a technical assumption that we need for the proof. But if I can, I would like to drop it, of course. Now we need this lambda for the theorem. And okay, let's look at the hydrodynamic limit. So this is the hydrodynamic for the bulk equation, something well known. That so if the dynamic is symmetric, this means that P is 0, so I don't have this term. Lambda is 0, I don't need any speed up because I'm considering the diffusive time scaling. So it's n squared T. Then the density of particle will converge to this heat equation. Now it's just a bulk equation. I don't care about the boundary. And if the system is asymmetric, so P is positive, then the system will perform a strong flux from left to the right. The formula is P times U times 1 minus U. And we need to consider the hyperbolic scaling. So here is NT and X. And the density, the particle density evolves with this hyperbolic conservation law. So partial T plus partial Xj is 0. So here, the symmetric part is speed up with n of lambda. But since we are considered on the short time, so it's a hyperbolic time, it's shorter than the diffusive time. So this will formally give me a term n of power lambda minus 1 of the diffusive term. And since I'm taking n to infinite and the lambda is smaller than 1, so this actually vanish in the limit. So this acts as a vanishing viscosity. So this part doesn't appear in the macroscopic equation. Okay, so these are the bulk equation. This is something well known. And what are we interested in is what is the boundary condition attached to this hyperbolic conservation law. So let me first give the imagine is that we expect the boundary-driven macroscopic equation is taking this form. So here, partial phi is a flux, so it should be u minus 1 minus u, but I would like to consider some more general case. So it's just a C2 function. And rho 0 is the initial data. This is not important. And the important thing is that the boundary condition is always a Dirichlet type. So it's on the right is some rho minus, and on the right is some rho plus. So rho minus, rho plus are all L infinite functions. So this is the equation we imagine. So which kind of solution we would like to consider? So first, as we know, this is a nonlinear hyperbolic equation. So the weak solution of this equation is not regular, and so it is not unique. And what we have to do is to choose a physically meaningful solution from all of these weak solutions. And this solution should be obtained through the so-called vanishing viscosity limit. So what is it? It means that I'm adding a small parabolic, perturbation here. So it's epsilon times the diffusive term. Then this becomes a parabolic equation, and of course it has a solution. It's a classical solution, it's well defined. Then I would like to take the epsilon to 0 and study the limit. I want to define the limit as the solution of this equation. So the first question I should answer is that, how to describe this limit clearly? So the first part of my talk will be completely PDE, that I would define explicitly what is the solution of this equation. This is crucial for the proof of hydrodynamic limit. Okay, so let's so to define this this limit, we need to introduce the concept is Lux entropy and the boundary entropy. So Lux entropy is a well-known concept. So this to say that if I have a pair of C2 function, S and Q, so S is the entropy and the Q is the flux associated to this entropy. The relation is that the derivative of Q is equal to the derivative of phi is a flux times the derivative of S. And I also demand that the second derivative, so I also demand that S is convex. So basically this is a convex Lux entropy. And in some times, so you will also see another definition of the entropy flux is a non-smooth one. So here I'm giving an example of the non-smooth entropy. The non-smooth entropy is that S is defined by as a norm of U minus R. R is any fixed number, and then Q is the integral of we get from this relation. So basically, these two definitions are almost the same because the non-smooth entropy is the limit of the smooth entropy, and the smooth entropy is always contained in the convex form of the non-smooth entropy. So basically, if you see the definition of the entropy solution with these two types of entropy is basically the same. And so this is the entropy, and to define the boundary condition, we also need this boundary entropy flux pair. So this definition is first given by Flex Otto in his PhD thesis. So the boundary entropy flux pair is a pair of two variable function S and Q. So the two variables is U and K. But basically, it means that the first variable is the same with a variable in the Lux entropy. So if I fix the second variable, then it is just a Lux entropy flux pair. And the second variable is the place I want to put the boundary condition. So I need to demand that the Q and S and its first order derivative will vanish when U is equal to the second variable. So Q equal to S equal to partial US is equal to 0. So this is just a definition of the boundary entropy. And of course, you can also have the non-smooth version of the boundary entropy. And the relation between the smooth one and non-smooth one is the same as I just mentioned. Okay, with these two definitions of entropies, so we can describe what is the solution looks like. So this definition is the entropy solution to star is the initial boundary problem of the conservation law. So this is the entropy solution. Okay.
Can I ask a question, Luce?
Yeah,
Could
sure.
you motivate the introduction of this pair of boundary entropy flux?
Boundary entropy flux. Okay, so okay, let's just see later because okay, just see later you will see the motivation. I'm sorry, just after this A. Okay. So let's continue here first. So first, this U is L infinite. So this is a regularity. So then the Lux entropy gives me the entropy inequality. This is also well known. It says that so if I for any Lux entropy and the test function, a smooth test function phi, this integral is always negative. So notice that here I'm taking the test function is compactor supported. It means that this entropy inequality doesn't see anything about the boundary and the initial condition. So this is just the entropy inequality inside the domain. And then we look at the initial and the boundary condition. So let's see the initial condition is something not so interesting. So let's just omit it. It's just like a continuous in L1. The important thing is the boundary condition. So we can see that the boundary condition says that for any boundary entropy flux S and Q, if I'm taking a continuous test function which is positive, then I will have these two inequality. So here the important thing is that I'm having an inequality here. So what does it mean? It means that, so if suppose that I have a solution which is continuous at the boundary, then so the limit for x to 0 for this U should equal to the boundary data, which is rho minus. And why I'm introducing this boundary entropy is that, so this boundary entropy, so if these two variables equal, this should vanish. So this means that if the solution is smooth at the boundary, this guy should be 0. However, now I'm having a sign. This means that this boundary condition is actually allow some kind of jump at the boundary. And this sign is controlling in which sense I can jump, because the jump should make so that this is minus for all boundary entropy flux. And the inverse sign happens at the right hand side, at the right side, so at 1. So these are the original definition of the boundary condition using the boundary entropy. It's made by Flex Auto. Okay, so okay, I didn't write here, but of course the entropy solution defined in this way is well defined. It means it exists and it is unique for the scalar case. It is unique. Okay, so I write this ABCD here. It's a very good mathematical definition, but you still think that, okay, I still don't know what really happens at the boundary, because here this essential limit, I cannot exchange this essential limit with this integral. Why? Because U is just a L infinite function. So this means that the essential limit of U for example, for x to 0 may not exist. So if so this means that I cannot exchange this essential limit inside to say something really about what is the limit of U Tx for x to 0. Fortunately, this problem is solved several years after this paper. So this is all PDE guys, there is a serious work on this. And finally, they prove an amazing result is that if U is the L infinity function, and the important thing is it satisfies the entropy inequality inside the domain, then it has strong boundary trace. What does it mean? It means that U0, so I have a U0 is an infinite is L infinite function in space, and U plus minus is L infinite function in time. So these functions are different from the initial data rho 0 and the boundary data rho plus minus in the equation. And then I can say that the essential limit of U for t to 0 and x to 0 and x to 1 does exist in the space of L1. With this, so why they exist is really because I have the entropy inequality. Because if I do not have this inequality, just have L infinite is enough. It's not enough to say that the limits exist. Once we have these limits, we can rewrite this boundary condition in a very simple way. Is that okay? So this is the initial one that we don't look at it. It's simple. The boundary condition now. So in the boundary condition, I can exchange the essential limit inside the integral and write the strong form. It means that if U minus is a boundary trace, and rho minus is the boundary data, the boundary condition in the equation, then Q U minus rho minus should be always negative for any boundary entropy flux Q. And for the other side, is inverse sign. So this D prime, now it's very clear that this D prime allows a set of possible boundary values of U. So this is very different from the diffusive case, because if this diffusive equation have a Dirichlet boundary, then the boundary value of U is fixed. But now it is not fixed. I can only set I can only give you a set of possible values, and hence, so U perform specific jumps located at the boundaries, which is known as the boundary layers. Yes, so these are really what is this boundary condition means. And let's give you a simple example. So now I'm taking phi to be the flux that we want to study is U times 1 minus U. And for simplicity, I'm considering a stationary solution with the small viscosity epsilon. Then I'm considering the boundary condition is 1/4 in the left, 5/6 in the left on the right. And then we can see that these are the stationary solution. And when epsilon is going smaller, we see that this stationary solution converges to the stationary solution, which takes the constant value, and the constant value is rho plus. This means that at the left side, I have a jump. I have a jump from 1/4 to 5/6. To formalize this jump rigorously, we can see that. So this is if we take this flux U times 1 minus U, then what is this boundary condition really means is that if rho minus is smaller than 1/2, then U minus should take the possible value of U minus is this one. So U minus is the essential limit of U at 0. And if rho minus is larger than 1/2, then U minus is this. So what does this mean? So this means that if rho minus is small, then so U minus is equal to rho minus. This means that the solution is smooth, is continuous at the left boundary. Or if it is not continuous, then it makes a big jump. This jump is U minus jumps to some big value. This is the case here. So it jumps from 1/4 to 5/6. And if rho minus is larger than 1/2, basically it doesn't make this means that this boundary condition doesn't make any sense. So U minus can be anything. if it's larger than 1/2. And on the, okay, sorry, this is not rho minus, this is rho plus, of course. And on the right side, I have something similar. Okay, so up to here, it's very clear that what is this boundary condition means. So this is really an entropy solution that satisfies the entropy inequality, and this set of boundary conditions is what we want to prove. Is it something clear for you that what is the solution looks like at boundary? If it's okay, I can continue. Okay.
Yes.
Okay, thank you.
I have a question.
Okay, sure.
Yeah. So I've seen that sometimes in a not completely rigorous way, what people do is that they match the fundamental solutions in the of the Riemann problem in the whole line with the boundaries.
Yes.
So do you get the same
yes.
the same solutions?
Yes.
Okay.
Mm-hmm. Okay. Okay, so this is a very clear description of the entropy solution to the boundary. And so finally, we need another definition, which is a weak formula. So this definition, I don't spend much time here. It's just so we will put the entropy inequality, the initial condition, and the boundary condition together to write a weak formula. And this formula is the formula that we really use in proving the hydrodynamic limit, because you know it's always the case that in the hydrodynamic limit, so it could be very hard to really prove something about the boundary trace from the particle system. So usually from particle system, we can only prove some weak formula, and this is a weak formula we want to prove. So this looks very complicated, but just to notice that the right-hand side is nothing to do with U. So it's just the initial data rho 0, rho minus, the boundary data rho minus, rho plus, and any fixed number k. So the whole thing is just deterministic. And what we need to do is to prove this entropy production is bounded by this deterministic number. And the test function, it's a test function. The test function phi now, you can see that it's in this space. So it can see the initial condition. It also can see the boundary condition, but it cannot see the end time t, and it's positive. And the remark is that, of course, the smooth entropy can be replaced by the non-smooth ones, and maybe the non-smooth ones with this weak formula is the most common definition of the entropy solution here. Okay, so this is a solution for the equation we want to study. And okay, it's half an hour later, I can finally go to the hydrodynamic limit. So the hydrodynamic limit, the result itself is easy to understand. So let's recall that we have a open asymmetric simple exclusion that generates L and T, and we speed up with N, so it's a hyperbolic time scaling. And we have some good initial density profile. Then this process has the hydrodynamic limit reads in this equation. So this is a hyperbolic conservation law with the boundary, the initial condition. So this is rho 0, not U0. So the initial condition comes from the initial distribution, and the boundary condition is something. It's rho minus, rho plus. We want to explain what is this. So the result is that. So my result is that. So first case is if theta is positive. Just remember that theta is a factor that regulates the strength of the reservoir. If theta is positive, then the reservoir is very strong. So it's a faster boundary case. Then, so these are all the technical assumptions, I need a very strong symmetric part, and I want to exclude those degenerate case. So these are all positive. Then we can have the boundary condition given by. So this is not a surprise. So the left density is a density of the left reservoir. The right one is the density of the right reservoir. So this is because the reservoir is very strong in this case. Another one is that, so if now theta is 0, so the reservoir is not speed arc, but alpha is equal to beta equals 0. So what is alpha? It's very hard to go back. I'm sorry. So alpha is the rate that the particle comes in from the left. Beta is the rate that the particle comes out from the right. So so if these two are both 0, so this means that the reservoir goes against with the flux. Okay. So in this case, I get the boundary condition is rho minus 0, rho plus is 1. And for the slow boundary case, we get the same thing. Okay, so this is the result. And I would like to say something more about this case, this degenerate case. So this case, if theta is 0, alpha equal to beta equals 0, or theta is minus, this means that the reservoirs do not provide sufficient support to the rightward flux. As I said, if theta is 0, if alpha equal to beta equals 0, this means that the particle cannot come in the left and cannot come out in the right. So this is against the rightward flux. And when theta is minus, then there's very few particles can come in the left. Very few can come out from the left. So it is still like it goes against the flux. So in this case, recall that we have shown that. So this boundary data essentially means that the solution has a boundary trace, and the trace is taking value from 0 and 1. So this is something sounds very strange. This means that even if I have nothing come in from the left, but the macroscopic equation can still stay at 1 at the left, also for the right one. And why is that happen is, okay, I didn't write anything here, but so I can just explain by words. So why it's happening is because suppose that we are starting with a configuration that has a lot of particles near the left boundary. Then, so the particles cannot enter from the left, but it can still go out from the left. So some particle will go out from the left. Then it will create a very small piece of empty sites near the left boundary. However, because the flux is to the right, so this small piece of empty sites will be blocked by the flux. And yes, will be blocked by the flux. And the size of this empty piece is not large enough to be observed in the macroscopic scaling. So this results to the phenomenon that even if alpha is 0, but the density can still be full in the macroscopic time scaling for some strictly positive time. Okay, so this is a strange phenomenon, but it's reasonable to say. So another thing it's easy to observe is that in this case, the total amount is conserved along time. This is easy because, for example, if theta is small, then this very few particle can exchange with the outside world. So the total amount should be conserved. There's a common thinking is that, can I define the entropy solution not with the boundary condition, but with this conservation law of total amount? But the answer is that the inverse is in general is fails, which means that the bulk entropy inequality plus the initial data plus this conservation law of amount is not enough to define a unique entropy solution. So we really need this boundary condition to make the solution well defined. Just the conservation law is not enough. This is a remark. Okay, so go back to this this case. We see that the fast boundary is basically solved. The slow boundary is also solved, but the normal boundary is we only know for the degenerate case. So what is about the general case for the normal boundary? So we can have some expectation for the boundary condition. So what do we do? So if we fix some epsilon, and we consider the weakly asymmetric simple exclusion given by this generator. So here is I have everything divided by n because I'm considering the diffusive time scaling. So it's n squared here. Epsilon is fixed. The hydrodynamic limit of this ASEP is known. It's this mixed diffusion translation equation with a very small epsilon. So the very small diffusive term here. And the boundary conditions is proved in this paper. So we know that if the reservoir is fast, then it's Dirichlet. If the reservoir is slow, then this boundary condition basically means that the flux, the gradient of the flux is 0. And when theta is 0, this is a kind of mixed boundary condition. So it's in some sense a Robin one. And what we should do here is we want to take epsilon to be equal to sigma times n of lambda minus 1. So if I take this one, then this gives the same dynamics of the asymmetric simple exclusion I studied. So because lambda is smaller than 1, so this guy should be very small. So I take this epsilon to 0 and study the limit. So what is the limit? So first, the limit of the equation is very simple. It's just the vanishing viscosity approximation I mentioned before. So this limit gives me the conservation law. And we can prove that no matter what is this boundary condition looks like, the limit always gives me some Dirichlet boundary condition. And the value of these boundary conditions is given in this way. So basically, the first case is nature. The value is the same. The last one is give me 0 and 1. And so you can see that this is the first case I proved in the hydrodynamic limit. This is a slow case, and this is a normal case. So this is basically if I erase this epsilon partial u, and then it will give me a second order equation, and you need to choose a meaningful solution of this equation for rho minus, and for rho plus is the same. So basically, this is a boundary condition that we should have for the case theta equal to 0. So this is a prediction. And should we know? Have we know any information about this result? The answer is yes. So actually, Badarang proved this equation for theta equal to 1, but he proved only for the first choice of rates. So what is the first choice of rates? Is the choice I made here. So is this choice when the particle jumps in accordance with the bulk asymmetry. So I have the way to jump back, but I cannot jump forward. Sorry. Okay. So here I write again what is this rates. And in this case, the boundary conditions are given by rho minus equal to rho bar minus bar, rho plus equal to rho plus bar. So if you put these values into this formula, It's a kind of computation, but it's simple. And finally, you get this formula. And his proof relies heavily on the projection of the asymmetric simple exclusion on Z with density rho minus bar on the left and rho plus bar on the right. So his proof is restricted on this special kind of boundary rates, and also can only do with the boundary rates that doesn't depend on time. So here rho plus minus should be two constants, cannot be an equation. And also we should observe that, so this rho minus is always smaller than the density of the reservoir, which is alpha over alpha plus gamma. So this is also nature, is because here is a balance between the reservoir and the rightward flux. So the flux, so the reservoir is going to set the density into this value, but the rightward flux will move part of the density from the left side to the right side. So finally, what the boundary condition is on the left is slightly smaller than this value, and on the right is slightly larger than this value. So this is also something nature. And if we do not take this special choice, so for general data, this general data means that this alpha, beta, gamma, delta are general constants or smooth function in time, or L infinite or non-smooth function in time, anything. So for general data and the theta equals 0, the problem is still okay. Okay, so up to here is my result. And I still have some minutes. I'm sorry, when is the seminar?
So usually it's you can still have up to 10 minutes.
Okay, then let's give a very simple sketch of the proof. So the proof basically goes like this. So we consider the empirical density, so theta n, which is the empirical density in time and space. And what we need to show is that the first is we need to show the ABCD four conditions for the solution. The first one is the L infinite function. So this means that I need to show that for good subsequences, then this empirical distribution, so this itself is a L infinite function, and it should have a limit also contains in the L infinite so it should has a limit also contains in the L infinite space. So this means that I should find some random L infinite function U, which has a distribution Q, such that the distribution of this empirical density converge weakly to this distribution Q along this subsequence. Once we have this, we should prove that Q almost surely my limit satisfies the entropy inequality as well as the initial condition and the boundary condition. And finally, we use the uniqueness of the entropy solution to say that this Q can only concentrate on the entropy solution of the hyperbolic conservation law. And this step is already done for PDE. So what we should do is only the 3 steps before, the 3 steps. Okay, so the first step is something known. We need to use something so-called the compensated compactness argument. So let's explain what is the point of the first step. So the first step, the point is that, so I know that theta n is uniformly bounded in the L infinite space. So it should have a weak star limit point. But the problem is that the L infinite space is not closed under the weak star topology. So I can only say that it has a weak star limit point in the larger space than the L infinite function, which is the space of Young measure. And what we need to prove in this step A is that this distribution on the space of Young measure actually concentrates on the subset of L infinite functions. And this is what the compensated components tells us. So this argument is developed by Josef Fries and a series of papers centered by Josef Fries. And the argument is basically goes this way. So I take a Lux entropy flux SQ and some smooth test function, which is compactor supported, so it doesn't see the boundaries. And I define the microscopic version of the boundary production in this way. And the sufficient condition for us to have a L infinite limit goes like this. So basically, we need to study carefully what is this production, divided into two parts. So the first part is vanished in the H-1 space. The second part is bounded as a measure. Once we can prove this, we can say that the limit exists in the L infinite space. This is something actually already done before. And the second step is to verify the entropy inequality, which is simple because we already studied this thing. And what we need is just to say that this is has a sign. And this one is basically very simple following the first step. And all these two steps has nothing to do with the boundary condition. And the boundary condition, maybe I can just explain the first case. So let's see the case 2. So this is a degenerate case where I should have a 0-1 boundary condition. So which essentially means that the essential limit of the solution is at the boundary takes values is 0 or 1. And how to prove this one? The key is to show an argument which say that the flux is 0 at the boundaries. So what is this? The argument is like this. So sorry. So this is not equal to 0. This is the limit of epsilon. When epsilon is small, this equals 0. And so let's see that. So this is the integral from 0 to epsilon, and then I divide by epsilon. So if the limit is 0, then I say that it is a 0 flux. So notice that in general, so this is a weak formula, which is not sufficient to prove this essential limit, because this is just an integral. And from the integral, I cannot say anything about the essential limit. But however, because we already proved in B that so U satisfies the entropy inequality, Q almost surely, then we should call for help for the PDE result here. Recall that this PDE result said that if an L infinite function satisfies the entropy inequality, then it has a limit at the boundary. So with this result, I have to go back again, sorry. Yes. With this result, we know that the limit almost surely has a limit. So the limit profile U almost surely has an essential limit at the boundary. Once we have this, then this weak form becomes sufficient to prove this strong form. So the logic is like this. So I have to first show the entropy inequality. Then I show the existence of the boundary trace. Then I do this weak solution, the weak formula, to prove this strong formula. Okay, the proof of the weak formula is actually pretty easy. It's because we see that if alpha is 0, then no particle comes in the left, or theta is minus, then very particle can enter from the left. This means that the flux from the left reservoir to the site 1 is very small. And since the flux cannot change over space a lot, this means that the flux at each bond in this macroscopic block near the boundary should also be small. Then I take the average of flux. Then I should get some integral like this. So I can say that, so here I have the limit epsilon to 0, and this thing, it should be small. And well, okay, so this is a proof for the case 2. And the case 1, I think I don't have really enough time to prove, but basically the case 1 is proved by the weak formula. And we need to take some auxiliary function and to modify the weak formula with this auxiliary function, and then to show that it has a sign. Okay, so I think I should stop here.
Thank you very much, Lou. So we can clap our hands if you want to unmute yourself and thank Lou properly. Okay, are there any questions? Are there any questions or comments from the audience? Let's see. So at the beginning, when I read the title, weak symmetry, I thought it was a typo, but it's now I understand what you mean. So
yeah,
you're superposing a symmetric with this sigma between 0 and 1.
Yeah.
This is how you create the asymmetry. Yeah.
A question. Can I make a question?
Yeah, sure.
So in your proofs, do you use coupling arguments like in some of these hydrodynamic methods, or is it completely free of coupling?
No, the proof is free of coupling because so if we want to use coupling arguments, basically we need to couple the finite dynamics with the infinite dynamics. And so to do this coupling, one essential thing is that the boundary density cannot change in time, and because we are considering the boundary conditions that change in time, so we're not able to do any coupling in this proof. So the proof is purely depends on the rely on the entropy method.
Another question related to the boundary conditions. So I didn't know that in this formulation in the boundary conditions you just take anything. I mean, you don't assume any type of continuity of the. So it's that that was something really known, or there is some detail there that one has to care about.
I'm sorry, can you say again?
No, it's just a curiosity about whether this is a kind of whether the literature, I mean, the current literature on boundaries in conservation law allows easily to deal with this time changing boundary conditions, or it's just or you really need to do some extra work from the probability point of view?
At least I should say in my proof, to assume the boundary condition is the boundary data is smooth in time doesn't help anything. So the proof is the same. Yeah.
Okay.
And Lou, sorry, so this lambda bigger than 5/7 and lambda bigger than 1/2, it's a technical condition.
Yeah, so the lambda is speed up the symmetrical part, and this means that I need very strong convergence to the equilibrium. So I need this lambda larger than 5/7 or 1/2, but we hope that it should be right even I do not have this lambda. Yeah,
it's harder to prove.
Yeah, but it's just hard to prove. Yeah.
And this is true for any alpha, beta, gamma, and delta. So where you have the maximum degree of freedom. Yes. And you can also recover Liggett's condition.
Actually, if we look carefully at Liggett's condition, so his condition looks like this. So if I have a lambda, then I should multiply this sigma with the n of power lambda. And then if n is large, this goes to something like symmetry. So in the linked condition, we cannot put this lambda. So I need to set lambda is equal to.
Yeah. Okay. Yeah.
So actually, these are two results that doesn't cover each other.
Thanks.
Yes.
Let's see. Are there any more questions or comment? Okay, I don't think so. So let's thank Lou again. Thank you, Lou, for this nice
Thank you very much.
presentation. And we update next Wednesday, same time, same place. Bye-bye.
Thank you.
Thank you, Lou.